Back again. We're talking about surface roughness now. Surface finish is intimately related to the function of a surface, and the proper specification of finish of surfaces, such as bearings and seals, is necessary. Surface quality specifications should be used only where needed, since the cost of producing a finished surface becomes greater as the quality of surface called for is increased. Generally, the ideal surface finish is the roughest that will do the job satisfactorily. So here's the symbols, and you can read those, what each symbol means on your own, and just be aware of it. Location dimensions. Okay, after you have specified the sizes of a geometric shape composing the structure, give location dimensions to show the relative positions of the geometric shapes. So in A and B, you have location dimensions. The corner in A, you locating the corner of that rectangle in the top view. In B, you're locating the circle in the top view. And then you go over to the right there, and those two drawings, and you have one front view and top view is good, and the one on the right is bad, simply because they put the dimensions in the front view instead of the top view. And then going down to the bottom row there, A, B, and C, I guess, you have different holes, like in A you have 5 holes, they're equally spaced, and that's how they want it dimensioned. In B, they only have 4 holes, they're in the same basic, well, they're a little different, they're off a little bit, but they only have 4 holes, and that's how you would do 4 holes. And on the right hand side, in C, you got an extra dimension in there, and it's piers, because they said it's over dimensioned. So yeah, bolt circle, I guess you could locate that bolt circle using that dimension on the right there from the center line up to that top hole. Mating dimensions. Mating dimensions should be given on the multi-view drawings in the corresponding locations. So if you look at A and B, you see locations of mating dimensions. How things should, these are assembly drawings. It's something we would have gotten into in chapter 14, but it appears we're not going to. But you'd have, like C would be a mating part. You have 2 parts. You have that bottom part and that shaft on the bottom up of there. So you have a dimension showing how far apart those should be located. This is called coordinate dimensioning. All your dimensions are coming from that upper left corner where it says 0, 0. It's sort of like a grid. Your XY coordinates, you start at 0, 0, and you go left with your dimensions, and then you go down with your dimensions, your vertical dimensions. And then you have tabular dimensions. This is usually done if you have more than one size apart. It's the same part, but it's different sizes. So what happens here is that you have part, or in this case it says detail 1, 2, 3, 4, 5. So you have 5 different sizes of this part, and depending on which part you're going to use is which dimensions you'll use. Okay. Okay, dimensioning for numerical controlled machining. A set of 3 mutually perpendicular datum or reference planes is usually required. These planes must be obvious or must be clearly identified. So this is numerically controlled machine is a machine that you can program, and you'd have them in machine shops. And back in the olden days when I was first doing this, you would have to do all your calculations and type it in, and it'd print out a metal tape with all these little holes in there. And you took that metal tape, put it into the machine, and it would do what you programmed to do. Now they use a PC to do all that. And a lot of times your CAD program, depending on which CAD program it is, you can directly load it into the machine, and it'll start go up and running and make your part. So, but you need to know X, Y, and Z, okay, for numerically control. Here's a drawing. I usually joke when they're in class. I joke around saying this is our final exam drawing, but this is an actual drawing. Okay, forging drawing of a connecting rod. Sheet metal bends. We've talked a little bit about sheet metal bends and sheet metal dimensioning. All allowances must be made for the bends. The intersection of the plane surfaces adjacent to a bend is called the mold line, and this line, rather than the center of the arc, is used to determine dimension. So you gotta allow for extra material, basically what it is. And these are the calculations that you would do to get that extra material when you do a bend. Okay, our last, notes, how to write notes, is usually necessary to supplement the direct dimensions with notes. Notes should be brief, carefully worded to allow only one interpretation. Notes should always be lettered horizontally on the sheet, arranged systematically. They should not be crowded, should not be placed between views if possible. Notes are classified as general notes when they apply to the entire drawing, and as local notes when they apply to specific items. So, here's examples of notes. I'm not going to go through all of them. I'll let you look at them. You got plenty of time on your own to look at these different type of notes and how they're done. Now, we're at the end of this thing, and you're probably going to find out when you look at these that I messed up, and instead of making about 4 or 5 YouTube videos, I'm going to have one giant YouTube video. So sorry about that, and but you can stop and start whenever you want. So I need to get rid of that. So that's it. Any questions, email me. Bye.